All right, wide area networks, take two. Okay, silly me, I started off on this chapter description talking to a dead microphone. All right, so here we are again. This time, hopefully, it's going to work a little bit better. And in this chapter, we're going to be talking about wide area networks, the technologies that are used in wide area networks, and we're going to talk about large businesses, small businesses, and home office setups, all depending on wide area network connections. Because there are times when you just need to communicate with the devices in your office or in your building. But for most of us, we do a lot of web searching, right? Whenever we need to research for a project, we don't typically open a book. We go on the web and try to find information. Not to mention, some of us do a lot of online shopping. Okay, so wide area networking, what is it? Well, this is connections not just in the building on a local area network. This is between businesses that are geographically far apart, over the internet typically, because the internet now connects pretty much every town on the planet. So you can go over the internet and then the rest of the haul you can go locally. Now, when you're defining or building a wide area network, this thing has to have capacity enough for your current users. You also need capacity for any additional users, because wonder if you bring in some more offices or more sites. So these things have to be able to scale for future growth. High-speed internet takes you pretty much anywhere you need to go. If you want a private network, you can have one. You might just have some offices in town that you connect together by a MAN, a metropolitan area network. And then software-defined WAN. This is where you have wide area networks that are controlled from a central location. And this requires like a workstation or a server that's running WAN management, WAN and LAN management software. And so here's a picture of a SD-WAN, software-defined WAN. So as you can see, we have, from a lot of these sites, we have multiple connections. We have broadband connection. We also have multi-protocol label switching, which is typically what we use for our internet connection. You can see some of these connections here are using MPLS. Now, this business about, you might be wondering, well, why would you need 5G LTE? Well, that typically would be for like a backup connection. Now, if you take a look at this picture, you're going to see there's branches on the left and the right of our central data center, and these represent remote or regional office locations. And each branch is going to have its own router or a software-defined networking edge device that connects to the wide area network. And these routers will dynamically manage traffic across the multiple network connections. At your data center, this is going to serve as your enterprise hub, and this would host your critical applications and your data, like your central data storage, like your customer databases and accounting, things like that. Excuse me. And this thing is also equipped with a SD-WAN router that can coordinate with the branch routers. And then up here at the top, we've got the internet. This is the main transport mechanism that connects everybody. We typically go across the internet using VPN connections, virtual private networks. And this enables us also to connect to cloud services if we need to. Like a lot of places use like Google Mail for their mail server, and that is a cloud service that's very popular. Okay, so business drivers. Why do we need to invest in WAN and software-defined WAN? Well, a lot of places now are migrating more and more of their services to the cloud. They're outsourcing. We also can use the software to enhance our network security, make sure only the right people are logging on. This also enables us to have a little agility. In other words, we can make changes to our network as needed. And we need network visibility. We need everybody to be able to see what they need to see on the network. And here's something else, affordability. We can't spend a ton of money on wide area networking if we're not going to get a return on that investment. We need this thing to either save us money or make us money, something like that. All right, WAN technologies in the 70s and 80s and early 90s typically consisted of modems. We had, whether you were at an office or at your home, you needed a modem. Modem stands for modulator demodulator, and what this thing does, it acts as a transceiver that enables your computer to communicate over long distances using analog signals. And home and office modems that were using the public switch telephone network, the maximum transmission speed those things could achieve turned out to be about 56K baud, 56,000 bits per second, which back in the day, we thought that was fast, and it was. The first modem I ever had was only a 300, it was only a 300 baud modem, which would be 0.3 kbit per second. And if you're just sending text documents back and forth, then that works. But, it was slow. There's no way you could have like web pages over a connection that slow. At 56K, we could do web pages, but they weren't super fast. Now, analog leased lines. If you have two offices and you need them to have a connection that's up all the time and has a little more bandwidth, then you can get with your local telephone service provider and they will provide you with what's called a leased line. It's like a telephone cable between two locations where both phones are off the hook all the time. And they're, whether somebody's picking up the phone and listening to it or talking on it, the connection is always there, whether it's getting used or not. Now, the downside to these lease lines, these things were expensive. Dedicated lease lines, they have a monthly cost that you're going to incur, and the faster that connection is, the more expensive it gets. And this is a picture of kind of how it worked. Here you are at your house with your computer and your modem, and you're communicating over just regular telephone lines to somebody's, it's like a closet full of modems. And whenever you dial up your service provider, then whichever modem is available will answer the phone and then establish the connection. And then you're connected to the central office of your ISP. Now for lease lines, like I said, you could get different speeds on these lease lines. Very common was what was called a T1 line, and that gave us 1.5 megabit per second, but it was very, very expensive. And you had to pay that cost every month, right? So it adds up over time. We also had T3 lines, and those were 45 megabit per second. Okay, so what am I looking? Oh, dang, sorry about that. I went back. Here we go. Okay, circuit switch networks, public switch telephone network and ISDN. Neither of these is used anymore for internet communications. They're just obsolete, so you're probably not going to run into that. Packet switches, packet switching network. What these things do is they look at the current state of the network and then they decide which path they have access to that's going to provide the fastest access right this minute. And the thing about these packet switch networks is the connections they use can change dynamically. So if they're using a line and it starts to get slow, they can switch over to a better line automatically. And this is how the internet works. So when you're downloading a file and it's like a couple of megabits in size or megabytes in size, it takes a couple minutes to download it. And during that download process, if the packets are going down a line and there's an issue, then they will automatically switch to another line. And the file arrives intact because TCP, remember, provides error checking and correction and also packet sequencing. So as far as we're concerned, we don't really care how the data got from point A to point B as long as it gets there. Digital transmission switches, these typically are used from service providers from one provider to another, and these things support DS 0, 1, and 3 digital communications. And then we have also satellite communications. And satellite communications these days are actually pretty good. We're going to talk about that in just a minute. Okay, satellite WAN connections. Satellite connections connect ground-based user terminals or facilities to a satellite that orbits the Earth, which then relays the data to another ground station, excuse me, connected to the internet backbone. It's basically a wireless bridge to the internet via a space-based satellite. And these satellites typically orbit about 22,000 miles above the Earth. So the distance between you and the satellite causes an increased latency. So these connections are never going to be as good or as reliable as a hardwired connection, but there are some times when it's something that you're going to have to use. Now, there are geostationary or Earth orbiting satellites. These things hover above the Earth and they orbit at the same speed that the Earth turns. So effectively, the satellite's always in the same place in the sky. These things typically operate about 22,000 miles up, and they have a latency of 500 to 700 milliseconds typically. And a couple of outfits that use this are HughesNet and Viasat. Now, they can connect pretty much any place you need to be. They're just not super fast. Now, there are also low Earth orbit satellites. Now, these are a little closer to the ground. They're typically between 300 and 1,200 miles above the Earth's surface. Their round-trip latency is lower, typically around 20 to 60 milliseconds. And you may have heard of Starlink. Starlink uses these low Earth orbiting satellites, and they typically have for their customers people that live out in rural areas. People that live in rural areas or people that live in RVs, mobile homes that move around a lot. Now, MEO, medium Earth orbiting satellites. These typically are, they kind of exist in between the GEOs and the LEOs. They will normally have a round-trip latency of 100 to 200 milliseconds. And these are used most often by the government, and they're also used by some enterprises. Not as popular with private users. Now, the GEO satellites, the ones that orbit, the GEO satellites that orbit at like 22,000 miles, those typically will have download speeds of anywhere from 10 to 100 megabit per second. The low Earth orbiting, like the Starlink, those things can hit up to 250 megabit per second. So not bad connection. Now, the problem with these things is reliability. The dish has to have a clear line of sight, a clear view of the sky. If there's mountains or trees or anything like that, other buildings, then that can mess up your reliability. You won't have as good of a signal. The other thing is this. These communications use microwaves, and when it rains or snows, or even if there's like really heavy cloud cover, then that can take away some of your speed and reliability. Okay, some more WAN technologies from the 1990s. Back in the 90s, we thought that SONET was really the cat's meow. This was a synchronous optical network, and this was pretty much the fastest thing that we could hope to use back then. What SONET does, it allows high-speed digital data to travel over long distances via fiber. So your signal, you don't have much signal degradation on a fiber link, and so the data transmitted is reliable and it's fast. And there's several different flavors of Sonnet. I'm not going to go over all of them, but the basic Sonnet gives you about 50 megabit per second, and then the fastest Sonnet that we ever had available was about 10 gigabit per second. Now, this business about asynchronous transfer mode, ATM, this was a switching technology that was designed to carry voice, video, and data across high-speed networks. And so typically what you would have is you would have ATM traffic traveling over a Sonnet network. So these work together. And the whole idea was to provide a reliable, high-speed connection, normally for businesses. Somebody would not have a Sonnet connection at their house unless they were a millionaire. This stuff was expensive. Okay, and this is just a little bit more about Sonnet, high-speed fiber backbone, synchronous digital transmissions. Now, with Sonnet, the transmissions were regulated by the atomic clock out in Colorado. So all stations that were in the Sonnet network were on the exact same time. So it used time synchronization to divide up its packets. MPLS, multi-protocol label switching. What this does is it allows devices to switch packets over an internal network. It operates at layer 2, but it only works. Multi-protocol label switching is just used by ISPs to communicate across their own network. And so typically whenever network traffic hits an ISP, then the ISP will give it an MPLS tag. And that tag allows that traffic to go through the ISP's network at a very high speed because it uses layer 2 switching instead of layer 3 routing. And then whenever the packet is getting ready to get handed off to the next provider, then the MPLS is stripped off, and then it gets transmitted to the next ISP via border gateway protocol machines that are using layer 3. But then once that packet gets into another ISP's network, then that ISP will use label switching to switch that packet within its own network. So MPLS is used internally by ISPs, and it just is a way to help speed up traffic across the network. This is a picture of a Sonnet setup. And you can see we've got these servers that are connected by a Sonnet ring. This one looks like it's running at 5 gigabit per second. All these are. Okay, so the Sonnet rings, you can think of that as like a metropolitan area network. And then for long haul, we use something else. And you don't find Sonnet that much anymore. It's kind of a bygone technology because these days everybody uses Ethernet over fiber. And this just shows MPLS connections. Okay, so we're going into the network at large. You can think of this as like the cloud. And so we're going in with our layer 3 traffic, our IP address. And then once we're inside the ISP's network, then they're going to use MPLS to move that packet around as quick as they can. You know, they're all about speed, because who wants to pay money for a network that's slow? You know, nobody. So the ISPs are very much interested in moving data through their system as fast as they possibly can. And this diagram here just kind of shows you how label switching is used in practice. So, you know, going from our workstation to our router that's going to let us onto the internet, we're just using IP, right? IP addressing. Then once we're inside the ISP, then label switching is used to get us to our destination. And then once we get to our destination, then we're switched back to layer 3 routing, and that's going to take us out to our server or other workstation, whoever it is we're trying to communicate with. Now this diagram shows how 802.1q and 802.1p tagging are going to work inside an Ethernet frame to support VLAN traffic and quality of service. The Ethernet frame has been extended to include this 4-byte 802.1q tag. And that's placed between the type field and the payload. Now, this tag contains several different bits. We use bits, either ones and zeros, to communicate what we want to do. So this priority, this is 3 bits, and this is going to be your class of service and your user priority. Then there's 1 bit here. The CFI is the canonical format indicator. You don't have to necessarily know that. This is used in bridging between Ethernet and token ring, which is not that popular anymore. It's kind of obsolete, but it's still there just in case. And then we got a VLAN ID. The VLAN ID consists of 12 bits, and that identifies which virtual LAN this traffic belongs to. Now this class of service identifier, this first 3 bits here, this thing can take several different values, either all zeros, because 3 zeros are just 0. And then if you have 3 ones, that is a 7 in binary. So the value here can be 1 through 7. If there's a 0 there, then this traffic doesn't have any significant priority. This is just going to be like email traffic, web browsing traffic, normal data transmissions, stuff like that. If it's a 1, then that's considered low priority. So that would be, like for FTP traffic or something like that. If there's a 2 in this slot, then that's considered high priority. That's like business critical data. And if there's a 3 there, then that means it's a VoIP, voice over IP signal, so it gets a little more priority. If there's a 4, then that indicates streaming or video conferencing, so that's a high priority. And then if there's a 5 there, then that is voice traffic. That is real-time voice traffic, and that's the highest priority. 6 and 7 aren't used, at least not yet. Okay, now this quality of service identifier. This is a little bit different. If we're looking at this quality of service identifier, we're going to have this type of service byte. Type of service is actually kind of outdated technology or outdated terminology, not technology, it's still good technology. But now people refer to this as differentiated services or diffserv field, as indicated right here. Okay, now the way this thing works, there's a whole bunch of bytes in an IPv4 packet header. Your data is back here. We have IP destination address, IP source address, time to live. Okay, so TOS is just part of the signaling that's used by IP traffic. And this type of service or diffserv code, it can be several different indicators. If it's a 0, then that's default, and that just indicates, okay, we need best effort delivery here. And so that would be for like web browsing traffic or email. If this DSCP, this diffserv code, is an 8, then that is just background traffic. So that would be like backups over a network, something like that, that you don't really care if it takes an hour to complete. It's not high priority. If there's a 24 here, then that means it's medium priority, and that would be, again, your business critical applications, your accounting information, stuff like that. If there's a 46 here, then that's going to indicate expedited forwarding, and that's going to be your highest priority traffic. So that's kind of a rundown on how that works. And here I've got it written out for you guys if you want to take a look. This diagram shows SD-WAN, kind of how it's set up. So we've got what's called a service orchestrator. That's like your top level SD applications. And then below that, it's communicating with an SD-WAN controller. And that WAN controller reaches out to the routers and switches that it's in communication with and helps orchestrate best effort traffic over whatever kind of network you're using. And some requirements of WAN management. Regardless of what kind of system you're using, you need fault management for sure. You know, like we were talking about in our network project, you need some way to indicate that like a network is down or a link is down. That would be referred to as a fault. Configuration management. This lets us change our WAN whenever we need to. We can add or delete switches and routers. And then accounting management. So suppose we've got an ISP that we're having to pay monthly to. Well, we want to keep a record of how much we were using that ISP and how much they're charging us. Performance management. This deals with the optimization of your LAN, efficiency, and the overall performance. And then security management. We want to make sure that only authorized persons are using our wide area network. And fault management requirements, okay, monitoring of all devices, and if one reports that it's having an issue, then we're going to have some kind of a response to that, like a failover, either manual or automatic. These systems need to be resilient and redundant, so that we have multiple possible lines connecting our different sites or devices. And then, of course, we need monthly reporting on like how much use there was and how much we spent. Some requirements of a configuration management system. Okay, so configuration identification. This tells us what items, and it could be software or it could be hardware, what items are going to be managed by our configuration. Now, each configuration identification has a unique identifier, and then we also want to establish a baseline configuration once we have a working system going. Auditing of the configuration, we want to make sure everything's documentation matches what we're actually doing and make sure that there's not been any unauthorized changes to the network, and we also want to ensure system integrity. Change control, that manages the process of requesting and improving and implementing changes to our network. Typically, there's going to be a group of people that review this kind of stuff and make sure it's going to actually work. And of course, every time we do any kind of change to our system, that thing has to be documented and tested, you know, just to reduce our risk level. Provisioning speed. How quick systems or resources can be deployed or updated after there is a change that's been approved. Typically, higher provisioning speed is going to be a more flexible and responsive infrastructure. Ticketing. Ticketing tracks requests, incidents, and changes through some kind of a service management system, and there are a bunch of those available. Those are third-party softwares that you purchase, and we also want to ensure accountability and traceability so that we can find out, like if something happens, you know, who did it and why did they do it. Not so that we can fire them or anything like that, just so we can figure out what they're trying to do here. Version control. If there's different versions of configuration files in the network, then we need to track that and manage it. There are several different tools that allow you to do this, and this is really essential for maintaining controlled development and operation environments. And then monthly reporting, you know, we're all about accounting here, right? So we want to find out the number of changes made, incidents that were caused by any changes to the network, and then we also want to have we also want to cover any compliance or auditing requirements that we might have. Now, on a wide area network, you're probably also going to have accounting management, accounting, asset inventory and management. Again, what devices, what software are we using? Service provider billing, make sure they're not billing us too much or billing us for services that we're not actually receiving. We want to be able to monitor the performance of our system. Now, service level agreements. This is where we have an agreement with an ISP or other vendor, and they say, okay, well, we're going to provide 100 megabit per second service guaranteed across this wide area network. Well, wonder if they're not doing that. You know, we have to check. A service level agreement says, and it's a contract, and if we are recording that we are consistently only getting like 70 megabit per second, then that means that the vendor is in breach of contract. You know, they told us they were going to deliver one thing and then they didn't do it. And then we can go to them and say, look, you know, you guys either fix this issue or else there's going to be lawyers involved. Vendor management, we want to make sure that we are paying everybody what we're supposed to. And then, of course, we're monthly reporting, you know, how administration likes to see their reports. Performance management. We want to make sure that we're getting the correct bandwidth, and it could be the ISP's fault or it could be ours. If we have our routers internally misconfigured, then we may not be using optimal bandwidth. So that's something we have to figure out. You know, is this our fault or is it somebody else's fault? Capacity planning, how many people are on our system? How many people are we going to have to support in the future? How far of a distance do we have to go? Where are our locations? So if we've got one location in Oregon and another location in Maine, then we're probably going to be using VPNs to go over the internet at large because, you know, getting a long haul connection that's dedicated is going to be really expensive for something like that. We want to monitor our systems, make sure that our throughput is what it's supposed to be. Traffic shaping, that refers to our quality of service and our class of service, like we were talking about just a few minutes ago. We don't want backup data to be eating up all the bandwidth that's causing a Zoom conference that the boss is trying to have to be, you know, to be stuttering or have a lot of jitter. And security management requirements. I'm not going to go over all this. You guys know what security is. We want to make sure that nobody's on our network that's not supposed to be, that people can't be stealing our data. Lots of ways to try to mitigate those issues. And if somebody ever does breach our system, we want to detect it. What is going to be our response? You know, can we shut that line down? And then if we do lose data, then do we have a plan for recovering? You know, because if somebody comes in and they try to ransomware us by encrypting our databases, do we have to pay, or do we have an up-to-date recovery, you know, like real-time storage in an alternate location? And so we can just say, well, we're not going to pay you because we've got everything backed up in a cloud somewhere. Enterprise WAN solutions. Typically, this is going to be big companies that have a lot of different sites. And we're going to need something scalable because you know how big companies are constantly acquiring other companies or selling off parts of their company. Security, we typically will have, like what we have here at CFCC is what's referred to as a stateful firewall. So if I issue like a web request, I send out a request for a web page, then whenever that web page comes back, the firewall is going to check its little database and it'll say, hey, is this web page coming from somebody that actually requested it? And it looks and it says, oh, okay, well, John Lee requested a web page, so therefore I'll let it through. A stateless firewall operates differently. It blocks all traffic by default. unless it is specifically tagged so that it can get into the system. VLAN capability turns out to be pretty important because a lot of times we have small departments that all share one switch and each department's on its own separate VLAN. VLANs help with your security because they don't let traffic from one local area network go over to another local area network, so therefore you can do things like separating personnel from billing, that kind of thing. Let's see. And here is a little network diagram. This diagram, it illustrates basically a metropolitan area network, a MAN. And what this thing is doing is extending Ethernet connections beyond the local area networks to multiple geographically dispersed sites. And what's going on here, you've got a high-speed network service provided by some carrier, some ISP, that uses Ethernet technology to link several different LANs that are in different physical locations. Each building here represents a different site or office, and each site is connected to the Metro Ethernet cloud through an Ethernet network hub. And the Metro Ethernet switch, which is located right down here, the central office Ethernet switch, this is providing connection to the provider's core network. So really this cloud represents the service provider's Metro Ethernet backbone, which kind of acts like a giant Ethernet switch to connect multiple LANs together. Excuse me. Sorry, had to get up and go answer the door. Okay, let's see. WAN solutions for small to medium businesses. Okay, high-speed internet access, of course, is a must. Security, again, stateful firewall. NAT, network address translation. Whenever you're setting up an internal, like here at CFCC, everything inside our building is on the 10 network, which is a private network. But going out to the internet, we have a NAT server, and that gives us our public IP address. VLAN segmentation, this is something you're probably going to need to separate different departments. And then a public-facing DMZ. Okay, we have a server, cfcc.edu. That thing is not connected to the internal network. This is our, I guess you would consider this our DMZ. So anybody that wants to can come to cfcc.edu, but you can't get onto the faculty or student network that way. You have to have correct login credentials in order to be able to access a lot of parts of our system. Let's see, connectivity to data centers and or cloud hosting facilities. Point-to-point protocol, is that still used very much? Once upon a time, we did this a lot. PPP connections were used on dial-up to enable us to run Ethernet over a dial-up connection and connect to, like from our house back to the office. And then nowadays, you're going to have a lot of VPN. If you're going long haul between, like if you've got an office here and another office in Charlotte, then the cheapest way to do it probably is by just going through the ISP and using a VPN. And as you probably know, a lot of sites now use multi-factor authentication. Like anytime I sign on to something using my Google Mail, then they want to send a notification to my phone, and then I have to check it yes, otherwise it won't let me log in. And then web content filtering. This is like from my office, if I try to go to, I don't know, like porn.com or whatever, I'm probably not going to be able to do that because that'll be filtered out by the firewall. So you can set up your firewall so that it filters out known sites that A, you don't want your employees looking at, and B, sites that are known to have a lot of viruses or Trojan horses. And there are a lot of sites like that. A lot of places that say, download our software for free. You download the software and then you wind up with a virus. And here's a sample Metro connection. And what we've got here, we've got customer edge routers that send their frames out to the provider's Metro Ethernet network. Now, the provider will encapsulate the frames with a VLAN ID so that everybody's traffic stays separately. You don't want business A mixing with business B. And then the network core will route traffic between sites based on the VLAN tags. And then from the user's perspective, all these offices behave as if they're just on one gigantic network, even though they're obviously physically separate. Metro area network. Small office, home office. You've probably all got some kind of internet access, like Spectrum or AT&T or MetroNet, whatever you happen to be using. We typically are going to be behind a firewall. Either you have your own firewall or the ISP provides one, and we're using NAT. So like at my house, I have two networks. I have 192.168.0.0 and 192.168.1.0. And so even though my house is just one house, there's technically two LANs in there. And VLAN capability allows you to separate your, like if you have like two offices, say you're running a small business and you've got two different offices, you got like a bunch of lawyers on one network and then the support staff is on another network, but you're all using the same switch. Because it's got 24 or 48 ports, so there's no need to buy separate switches for the different LANs. You can just divide them up into virtual LANs. Bandwidth rate limiting, that is a thing actually. So if you're going through a carrier, then they will throttle they'll throttle your speed based on how much you've used that month. So if you exceed your gigabit limit, then they might slow you down. And that's part of your SLA, your service level agreement. So you knew about this when you started out. Wireless access, typically these routers that are used in small businesses have got wireless access built in, and you always want to use WPA2. You might use WPA2 Enterprise if you want to have central management of everybody's user ID and login. Stateful firewall, we talked about. Stateful just means that incoming traffic will be allowed if it's reply to outgoing traffic. But if it's just incoming traffic that's non-solicited, then it's going to get blocked out. Remote access with VPNs. And then web content filtering, we talked about that too. And here's just a little sample. Now, typically your switch and your router are going to be one device. You're going to have something like a Netgear Nighthawk or an Asus or whatever brand you like. It's going to have some switch ports that you can connect to with a hard line. And if you have more devices, then it will support. Because a lot of times these all-in-one devices, they'll only have like 4 or 5 network ports. So if you want to expand that, you can. You just plug in another switch, and then you can have pretty much as many devices as you want. Now, when these devices are all competing for bandwidth, you might run into a minor issue because your cable modem can probably only support like 200 or 400 megabit per second. So if there's just one person on the network, then they've got the whole thing. But if you've got like 6 people that are all trying to watch videos and surf the net at the same time, then they're going to get slowed down because your aggregate bandwidth is not going to support that. And okay, data over cable service interface specification, which is also referred to as DOCSIS. And there's several different flavors. I didn't put in like DOCSIS 1, DOCSIS 2 because very few people use that anymore. Nowadays, standard cable internet service is going to use DOCSIS 3, and that's going to give you 100 megabit per second up to 1 gigabit per second download speed. And this is an asynchronous connection. So your download speed is really high, your upload speed is relatively low. Now, if you get a business class connection, through Spectrum or whoever your ISP is, then you can make these numbers match. So you can have like 200 megabit per second download and upload. And you're probably wondering, well, why would you want that? Well, if you host your own web server, like say you've got a little home business and you've got a web server that you manage yourself, then you want people to be able to pull data off your server as fast as possible. So in that case, and that's what we have here at the school, because some of our web services are cloud-based, but then some of our servers are right here in-house. So we need to be able to send data as fast as we can receive it. So we have 1 gigabit each way. Now, that's not, you don't typically get a full gigabit because some of the firewalls are deliberately throttled down to like 200 megabit per second so that they don't swamp the network connection, because we have so many different sites using the same ISP connection. There's also gigabit cable, DOCSIS 3.1. That gives you 1 to 2 gigabit per second download. And then the new standard, DOCSIS 4.0, I don't think that that's available here yet, but it might be. I think maybe Earthlink, AT&T, I think they say that they can get you a 5 gigabit per second, line. But it's not available everywhere, and it has to be over fiber. I'm sorry, it can be over coax, but it's usually over fiber. And that basically is the end of our little chapter on wide area networking. And I know this is kind of a long video, it's like 46 minutes, but hopefully it helped clarify some of the points in this PowerPoint and will help you in your studies. All right, thanks very much, and I'll see you in the next one.